Okay, welcome everybody to the public defense thesis, Jose Acuna. And my name is Per Lundqvist. I'm professor at Energy Technology. I will act as a chairman for this session. So my job here is to get this going in a good way, to welcome the committee and the opponent and make sure we have a good procedure. So on behalf of the Educational Board of School of Industrial Engineering and Management, I'd like just to go through a few small things. First of all, mobile phones, okay? It's like the theater or concert hall here. Okay, so the title of the thesis is Distributed Thermal Response Test, New Insights on U-pipe and coaxial heat exchangers in groundwater-filled boreholes. If you want to have a thesis to go along, you can pick it up here. If you don't have it, I prefer if you do it now. Or if you can, if anyone would like to have a thesis, please. There's only one door. The room is not ideal, so there might be some people that are slightly late, so we hope they can sneak in. So we try not to take too much notice of them. We have Jose here is, of course, the main person here to defend his thesis, but we also have a very distinguished opponent, faculty opponent, Professor Jeffrey Spittler, School of Mechanical Engineering, Oklahoma, US. So you will perform later. We will start, I will soon go through the procedure more formally. We also have an evaluation committee of 3 people. So we have Professor Bo Nordell, Luleå Technical University. We have Professor Ole Andersson, Geoenergy, Lund, Technical University, and we have from KTH Professor Folke Björk from Building Technology. So it just translates pretty much straight. Building Technology. So we have a very good committee and we have a very good opponent. And the principal advisor for Jose Acuna has been Professor Björn Palm, who is busy handing out thesis. Sorry for the overhead slides. I said that probably this is the last time we're going to, this is a very old and traditional procedure. We have been doing this in the same way for 175 years, so that's why we stick to this dusty machine here. But I will try to advocate a switch to something more modern. Anyway, the procedure here is first we are soon through the opening, and then Jose will present his work for about 35, 40 minutes, and then there will be, after that, we have a discussion between the faculty opponent and Jose, and the rest of us are just audience at that part. And when the opponent feel that he's done, or there's actually no time limit for it, so I hope you brought some sandwiches and things, because this could take a while. And then after that part, we move over to the committee for some questions, and then at the end we open up for everyone in the audience to also ask questions. And after that, we will close this formal session, and the committee and the opponent and the supervisor and the chairman will meet in a closed session and discuss the thesis and the verdict. And I think we will do that meeting in a nearby. Björn is going to find. So that's pretty much the procedure. So by that, I would we can say that the defense is open, and I will hand over the word to you. Good luck.
Good morning, everyone. Thank you for coming. So my thesis title, Distributed Thermal Response Tests, New Insights on U-pipe and coaxial heat exchangers in groundwater field boreholes. I hope you all have it with you. This thesis is structured as shown in this slide. I have 7 chapters. Few new results which are not in the papers, and then final conclusions based on these specific objectives set for each heat exchanger. So my general objective was to suggest methods for reducing the temperature difference circulates and exchanges heat with the ground. And depending on the pipe geometry, there are different borehole heat exchanger types. The common one is the so-called U-pipe, one pipe going down and one pipe going up, as you can see in this prototype. And then there are and these are, of course, the surrounding ground, the filling material between the ground and the collector pipes, which in this case is groundwater, and therefore this word in my title, groundwater field boreholes, and then the collector pipes themselves, and then the fluid circulating inside, so-called secondary fluid. And to study the performance, the thesis has mainly focused on the measurement or the determination of the borehole thermal resistance, a very well-established parameter used for many years to measure the performance. And this is called RB. You will see this along my presentation many times. And depending on this value for each heat exchanger, for a given heat extraction rate, according to this diagram, just as an example, you can see what fluid temperature or secondary mean fluid temperature you'll get up in the or in the borehole, in this case for the heat extraction case. The method used for the tests is the very well also established thermal response test method, which consists of injecting or extracting heat or with a constant rate during a certain period of time in order to get steady flux conditions. And as you see in this diagram, temperature versus time, I am plotting a curve for the borehole wall, which is the temperature exactly at the interface or a bit into the interface between the borehole and the rock, and a mean fluid temperature. So as you see, these two temperatures increase in time. The difference between them is a measure, you could say, of the borehole resistance. The difference between the undisturbed ground, which is the baseline here, and the borehole wall, which increases in time, is the ground thermal resistance, and is very closely linked to the ground thermal conductivity, which is also one parameter found in my experiments. The particularity of my tests is that I have not done just a typical response test, but I have instrumented several borehole heat exchangers with optical fiber cables that go inside the pipes, also inside the groundwater, and even in some case at the borehole wall. And through these fiber optic cables, I connect what is so-called distributed temperature sensing instrument, which sends us laser. And as this laser travels, you get some light reflected back, which gives information about temperature. And as this is done, I get the whole temperature profile along the depth for any time instant during the response test. And this I have called distributed thermal response test. So as you can see here, I have an illustration of time in the horizontal axis, depth in the vertical axis, and then I have an illustration of how the precirculation period goes, the heating period, and the heat recovery period at any depth during the whole period of time. And the heat recovery period is giving us the information about the thermal conductivity of the ground. The heat injection period is used mainly for the determination of the thermal resistances. Here you can see a picture of one of the borehole heat exchangers having the fiber optic cables coming from the two pipes, and in this case for the borehole wall. So during this test, both the borehole resistance and the ground thermal conductivity are determined at many instances along the borehole depth, thanks to these measurements. This was the background and a presentation of the first two chapters of my thesis, and now I will go into the results, which I will divide per borehole heat exchanger type. So starting with U-pipe borehole heat exchangers, my objectives were the determination of the local ground thermal conductivity and thermal resistances in U-pipe heat exchangers, comparison of the thermal performance during forced and natural convection conditions, and to measure and observe the effect of varying the volumetric flow rate and the thermal and observe the thermal distribution along the depth in U-pipes. And these experiments were done in two installations, two borehole heat exchangers, which are in the project called BHE4 and BHE7, borehole heat exchanger 4 and 7, respectively. And these heat exchangers had a groundwater level of 5.5 meters. This is the diameter. You can see the depth for each of them. The fluid used is the same, having an aqueous solution of ethanol. And then the heat exchanger is a U-pipe, as shown here, or a U-pipe having as spacers separating the pipes, as shown here. And these two heat exchangers were instrumented with an optical fiber cable going down, turning in the bottom and coming back inside the pipes, and then one optical fiber cable also outside the pipes. And this is illustrated in this chart. And here you can see two pictures of the heat exchangers. For borehole 4, the local analysis is done at 12 different sections, which I illustrate in the picture to your left-hand side. So 12 sections, 20 meters long each, as illustrated. First paper appended to my thesis has a title of Distributed Thermal Response Test on a U-pipe borehole heat exchanger. And this test consisted of injecting about 9 kilowatts power during a couple of days to this heat exchanger. And here you can see the period of time when I was measuring the undisturbed ground conditions, then a period of time during precirculation of the fluid without heat injection, the heat injection period, and the thermal recovery period. And as I said, the thermal recovery period is used for the determination of the ground thermal conductivity, the heat injection for the determination of borehole resistance. And if we want to see each of these periods in time along the depth, I'm illustrating several instances in the chart to your right-hand side, where you can see the temperature profile along the depth at different moments. And the same thing for the heat recovery period. You can see the temperature profile along the depth somewhere in this period at the beginning of the thermal recovery phase, showing both the temperatures in the groundwater and in the secondary fluid side, and showing that there is almost no temperature gradient radially inside the borehole during this period, which is the reason why we decided to use this period for the thermal conductivity determination. The result of this paper was thermal conductivity is varying slightly along the depth, but still giving a very homogeneous picture of the thermal conductivity. The average of these conductivities is in very good accordance with the one found during the thermal response test, where only measurements on the top of the borehole are done. And also slightly higher values at the lower part of the heat exchangers as compared to the upper part of the heat exchanger. The borehole thermal resistance is found at each section is presented here, and you can see some slight variations as well, possibly due to some pipe shifting position inside the borehole. And these are measured for this volumetric flow rate and at this temperature level. The second experiment on U-pipe borehole heat exchangers consisted on a similar test. The borehole heat exchanger is divided again in these 12 sections. But at some point, after the injection has been running for a while and I have measured my values during the typical DTRT conditions, DTRT stands for distributed thermal response test, then I am injecting at some point nitrogen bubbles in the groundwater side to get a forced convection condition in the groundwater. So this is an injection point located 85 meters depth. So from 85 meter depth and upwards, there will be moving or some kind of two-phase flow in the groundwater side of the boreholes during this period of time. And you can see that the whole temperature profile in some ways is changing because of this. And if you want to compare this, I don't know how visible it is, but what you see here is a picture at 16 meter depth, or a video filmed during the typical thermal response test conditions where groundwater is having the so-called free convection state. Here there are, at this moment, started the bubble injection, and this picture will become a little bit clearer in a minute. I think the camera was covered by some kind of air. And then you will see that the groundwater is much more perturbed or disturbed. And the idea with this test was to compare this free convection state with the forced convection state. So if we compare the temperature profiles along the depth, if you have on your left-hand side will be a typical profile during the heat injection period without the nitrogen injection. And on your right-hand side, you have the temperature profile during the nitrogen injection. And as bubbles are injected in the groundwater side, you can see that from the injection point, which is more or less at this depth, the groundwater temperatures are homogenized due to this movement. And quantifying the implications of this, if we start by looking at the picture on your right-hand side, this is the fluid to groundwater thermal resistance plotted before the nitrogen injection, during the nitrogen injection, and after. Before and after, they give almost exactly the same result, which is logical, but during the heat injection, above the injection point, which is in section 4, the thermal resistance between the fluid and the groundwater significantly decreases. These values can all be put in perspective as compared to my results presented in paper 1, where I have the borehole thermal resistances, and then you can see the borehole resistance together with the fluid to groundwater thermal resistance, and even a groundwater to borehole wall thermal resistance calculated also as a standard thermal response test. And you see the proportions of these numbers there. What happened locally, I am illustrating with these 3 charts. Section 2 is above the nitrogen injection point. Section 4 is exactly by the injection point, and Section 5 is under the injection point. At Section 2, what happens, if you see this graph, I am presenting temperature difference between the fluid and the groundwater, and on the right y-axis, the thermal power per meter. And you see that the temperature difference decreases at the same time as the thermal power increases. On Section 4, which is by the injection point, the power stays the same, but the temperature difference decreases. And under the injection point, both the power and the temperature difference decrease. And this explains the reason why the distribution of the fluid to groundwater thermal resistance is as shown here. Going forward into the second heat exchanger tested here, I have done a thermal response test with fixed heat injection during a period of time where I imposed different flow rates. And here you see the fluid temperature profile as well as the groundwater temperature profile at these different conditions. And you can see how the dependence on the flow rate for a given heat rate. Quantifying this difference between the groundwater and the fluid will give us a picture also of the fluid to groundwater thermal resistances in these heat exchangers as a function of the different conditions tested. But before I go to that, I would like to show you that the conditions given the changing flow result in changing Reynolds numbers even along the pipes. And you can see here the different cases, Reynolds numbers changing abruptly between the different cases as expected. But if we go to a very low flow rate, then it might end up in laminar conditions on the way upwards for this specific case. And this gives, in terms of the heat transfer coefficient, low heat transfer coefficients as expected, which is also equivalently measured as a thermal resistance inside the pipe, fluid to inner pipe wall thermal resistance. During these tests, I have measured, of course, the thermal power as a temperature difference at each section of the borehole along the U-pipe. And we can see here that on the downgoing pipe, much heat is injected at low flow rates at the top. And then on the way upwards, as shown here, the heat flow is negative, meaning that we have a large thermal shunt flow. At the larger flow rates, we have a slightly better picture of the heat flow distribution. And we can do average per section on this, so we know exactly how much goes to the ground. And this becomes the picture shown to your left-hand side. So we see that the power distribution along the depth is slightly changing with the flow rate, still can be considered rather even as long as the flow rate is relatively high. At very low flow rates, there is a tendency to be unevenly distributed. And the temperature difference between the groundwater and the fluid that I showed you before, and these rates give us a picture of the fluid to groundwater thermal resistances along the depth, which you can see here for the different flow rates, resulting not to change much with the flow rate. So from the U-pipes borehole heat exchangers, my conclusions were variations in the ground thermal conductivities and the borehole thermal resistance and the local thermal resistance were found at the local level. The average result from the DTRT is in good accordance with the standard TRT or thermal response test in terms of the thermal conductivity. There are larger thermal conductivities found at the lower part of the borehole as compared to the upper part. And this actually had to do or was in some way indicated by the larger or the faster thermal recovery of the ground. And some indications of the borehole deviation also observed indicated that the ground might change after a certain point in the borehole. The second conclusion, injecting nitrogen bubbles in the groundwater eliminates the radial gradient and increases the specific flow, the heat flow. And then the fluid to groundwater thermal resistances is about 30% lower than during the natural convection conditions. The fluid to groundwater increases with decreasing temperature, and the fluid to groundwater shows a similar trend to the borehole or the local borehole temperature. Regarding the heat distribution, we can see that, as I said, the heat distribution is quite even as long as the flow rate is high enough, or if there is no forced convection. We saw that with forced convection, the heat is redistributed in the borehole. Going forward, I present results from another EU pipe heat exchanger, but in this case is a EU pipe heat exchanger having CO2 or carbon dioxide as a secondary fluid and not having a pump for circulation. And the idea with this test was to acquire a better understanding of the operation of this heat exchanger, which we managed to make work. And these are the characteristics of the borehole. I have an insulated downcomer pipe on 22 millimeter, and then a 28 millimeter riser pipe, to which I have attached a fiber optic cable also along the whole depth. So we are going to measure here outer pipe wall temperatures in this heat exchanger. The high pressures inside this pipe made it difficult to install the fiber inside. So the summary of the second paper, which has as a title, Distributed Temperature Measurements on a U-pipe thermosiphon borehole heat exchanger with carbon dioxide, this paper consisted on looking at the operation of this heat exchanger and trying to explain the behavior. So we see here a period of time where nothing was happening in the borehole. These are temperatures inside the borehole during about 7 hours or 8 hours. And then we allowed the heat pump to start and start extracting heat from the ground. And then we see the different cycles as the heat pump goes on and off. And we have picked one cycle and specifically one instant to study what happens in the CO2 side. So at some point here, I'm showing the cycle starting at 1532, this specific day, which is the cycle starting there, and the temperatures decrease, and then you can see how the profile changes abruptly as the heat pump starts, and then decreases slightly during the heat extraction period as the temperatures in the ground becomes colder. And the heat recovery period after the heat pump goes off. One thing that we see in the picture in the middle here is that the temperatures along the riser are relatively constant. There is a slight increase at the lower part and then slightly constant. And this gives an indication of the two-phase process taking place in the riser pipe. So two hypotheses were raised in this paper. The first one is some evaporation may start to take place at the downcomer, resulting in an extra pressure drop that will be reflected on the temperature levels. Or the second hypothesis, depending on how ideal the downcomer insulation is, the liquid may be subcooled at the bottom. And here you can see the pipe, the studied profile a bit closer, now including a measurement with a fiber cable that was hanging free in the groundwater side. So we can see the riser pipe temperatures in red, as I said, increasing slightly until about 30 meters depth, and then being relatively stable the rest of the length until the groundwater level. And these temperature differences gave the possibility to calculate heat transfer coefficient between these two measurement points, or a pipe to groundwater thermal resistance, as you could see. And then we could see that the heat transfer coefficient was actually higher from the point where we saw the temperatures to be relatively more vertical, giving an indication that perhaps the flow, the phase change period is in that section. And the increase here is an indication that the fluid is still in liquid phase, perhaps, and then it was subcooled at the bottom, still raising its temperature as it goes up until it reaches the saturation point. And this was confirmed with a model not included in the thesis, which reinforced this hypothesis. The conclusion of this work was that the total temperature change along the riser was 0.6 degrees, mainly occurring in the lower part of the pipe, and the CO2 seems to be subcooled at the bottom of the downcomer as a consequence of the increasing pressure and the pipe insulation. And assuming an even heat distribution, this heat distribution was based on the measurement on the heat pump side of 70 watts per meter. The lower thermal resistances are measured in the upper part of the riser, giving an indication of the evaporation conditions in this section. I go forward to pipe-in-pipe borehole heat exchangers now, the first coaxial type that I will present. My objectives in this chapter were the determination of the effective and local thermal resistances inside two pipe-in-pipe borehole heat exchangers having a flexible external pipe at different volumetric flow rates. Implementation of a method to measure the borehole wall temperature, experimental evaluation of insulating the central pipe in these heat exchangers, and assessing the performance of this heat exchanger during heat pump operation. And these experiments were done in two heat exchangers internally called in the project as BHE9 and BHE10. And these two heat exchangers are illustrated here. In the left-hand side is the BHE9, is a central pipe and an external pipe. In BHE10 is the same, but the central pipe is insulated until a certain depth. And the external pipe, or the particularity of this heat exchanger, is that the external pipe is flexible. I have a sample here of the flexible external pipe. So this pipe is sent into the ground, filled with water, and as it fills with water, it expands and covers the whole borehole volume, and it attaches to the ground. So the fluid can travel in a closer contact with the borehole wall or the ground. Here are the dimensions of the borehole, and the fluid used in these heat exchangers has been water even during the heat extraction periods. And if we want to see how this pipe looks like inside, I can show this quick video here to show you how the borehole looks like once this external pipe is installed. And you can even see at some moments a fiber optic cable that is installed between this pipe and the rock wall, which is pressed there. And this is the method that I claim can be used to measure the borehole wall temperature. And in this picture, you see one of these two heat exchangers. There are two fiber optic cables, one going down through the central pipe. It comes back through this annular channel, and then one fiber optic cable installed between the external pipe and the borehole wall. The tests in the heat exchanger were also distributed thermal response tests. In this case, two tests presented on the chart here. You see a first heat injection period with a flow rate of about 0.6 liters per second, a thermal recovery period, and then a flow rate slightly lower and the same temperatures. I'm plotting in different colors the borehole wall temperature, the fluid inlet and outlet temperature, and other temperatures which I discuss in the paper regarding which one is more convenient for the calculation of the thermal resistance in this geometry, including the annulus temperature and a true mean. And for the local analysis, this borehole heat exchanger is divided in two sections. And these two sections are the first one from 17 to 77 meters, and the second one 97 to 157 meters. And the reason of this division is mainly because in borehole number 10, as compared to borehole 9, I have insulation all along this first section. So I wanted to see if there were some differences in section 1 because of this. As on on these two pictures, I show the typical temperature profile in these two heat exchangers. You can see that the fluid goes during the test downwards and raises here. And I'm presenting here the borehole wall measurement. You see the temperature difference between the annular fluid, or the fluid through the external pipe, and the borehole wall is relatively low. Also for BH10. And I also plot or illustrate the in and out average projected all along the depth, a true mean value, which are then used for a estimation of a borehole resistance. So depending on if we use the annulus temperature, which is actually the only one having thermal contact with the borehole wall, we get the thermal resistances for this test seen in bolded letters here. But if we take the inlet and outlet mean, we get this so-called effective borehole resistance of 0.03, more or less, in average. Or if we take a true mean, it gets these values. And I suggest to use, for comparison with other heat exchangers, of course, the effective borehole resistance, but for the local analysis, the annular to borehole wall thermal resistance. And this, given the fact that the flow doesn't have, or the fluid doesn't have any thermal contact between the central pipe and the borehole wall directly. So these are thermal resistances at the local level for section 1 for the 3 heat exchangers, so which we see that they are about 0.01 Kelvin per meter watts. To put this in perspective, the borehole resistances in EU pipe heat exchangers were about 0.07. During these 3 tests, I am plotting here the typical instantaneous temperature profiles in these heat exchangers, and you can see the distribution of the heat as the fluid travels downwards. And we can see that for borehole 10, for example, which has an insulated central pipe, the fluid in the central pipe does not release as much heat as when the pipe is uninsulated, giving an indication already there that the insulation is, of course, doing some effect as expected if it works. And on the lower part of the borehole, the profiles are similar, but on the way upwards, there is a radical difference between BHE10 with the insulation and the BHE9, also evidencing the presence of the insulation, increasing the heat injection at this later upper part of the heat exchanger. The temperature, the Reynolds numbers in this heat exchanger were very turbulent on the way downwards in this central pipe, and close to Reynolds of 3,000 on the annular channel. And this gives heat transfer coefficients changing drastically between the down and upgoing directions. During heat pump operation, I did some tests allowing the flow rate to change, and I have the temperature profiles for these 3 cases, 0.4, 0.5, and 0.6 liters per second. So this is now heat extraction, so the fluid goes in here, and this is borehole heat exchanger number 10, and goes up here. And here, to the right, you see the borehole wall temperatures for this specific instance. With these measurements and the specific heat extraction rates, I calculated borehole resistances, or which I call annular to borehole wall resistances, which are, for the heat extraction cases, about 0.025 Kelvin meters per watt. It's compared to about 0.015, which were for the heating case. The conclusions from pipe-in-pipe heat exchangers. The effective borehole resistance on 2 pipe-in-pipe borehole heat exchangers having a flexible external pipe was measured to be between 0.027 and 0.035 Kelvin meters per watt. The temperature in the annulus should be used alone, disregarding what happens in the central pipe when calculating the local thermal resistances, which results on a borehole resistance at the local level of about 0.012. Installing an optical fiber cable between a flexible external pipe was demonstrated as a method to measure the borehole wall temperature. Then the insulation induces a change in the temperature profile, the insulation of the central pipe. and decreases to some extent the thermal shunt, or the thermal contact between down and upgoing channels. The heat flow was also found to be evenly distributed along the depth in this type of heat exchanger pipe at the given conditions. And the low borehole thermal resistance allowed using water as a secondary fluid. The heat extraction cases were using water as a secondary fluid. I will lastly go through the measurements on the multi-pipe heat exchangers. And these heat exchangers, on this heat exchanger, the objectives were the evaluation of the thermal performance of a novel type of multi-pipe heat exchanger, including the local thermal conductivity of the surrounding ground, assessment of the effect of insulating the central pipe and quantification of the thermal power distribution, and the determination of local thermal resistances at different volumetric flow rates. And the tests in this heat exchanger were done on a prototype, which cross-section you can see here. We have a central pipe similar to the ones used in U-pipe heat exchangers with an insulation layer, and then several smaller pipes which are parallelly coupled. This borehole heat exchanger looks in miniature as shown in this prototype. So this is the top part, the bottom part, and you can see more or less how it looks along the depth. And these are the dimensions of the tested borehole. There were also, of course, distributed temperature measurements involved here, and there is a fiber optic cable going through the central pipe, returning at the bottom, and going through one of these external pipes, as illustrated in this figure. And here you see the pipe dimensions, and the external pipe dimensions were 16 millimeters times 2. So the inner diameter is 12 millimeters. Here to the left you see the undisturbed temperature profile, which is a bit particular for this heat exchanger. The paper published on this heat exchanger type has as a title Distributed Thermal Response Test on a Multi-Pipe Coaxial Borehole Heat Exchanger. And this paper presents results from 6 DTRTs continuously done, which I present in this chart, temperature versus time, as well showing the injected power at each of these tests and the volumetric flow rate. So we can see the flows change to some extent between test to test. I wanted to test the performance at different flow rates and even at different heat extraction rates for the same flow. This to study also possible effects of the natural convection. And the borehole for the local analysis was divided as shown in picture to the right-hand side. So it's 4 sections, 20 meters long each as well. And you can see a particularity here that the pipe through which the optical fiber cable was inserted had to be changed in dimension due to practical issues. So the sections 1 to 3 have a slightly larger measurement pipe, which ended up not to give any differences, as you will see. Anyways, the heat flow distribution, I am presenting here for the lowermost section and the uppermost section, which are illustrating how or what happens in these heat exchangers. So if you see here the curve for the total injected power at the uppermost section and the lowermost section, you see that more power is injected at each test at the top of the heat exchanger, and very much lower at the bottom of the heat exchanger. The heat distribution was then found to be very unevenly distributed as compared to pipe-in-pipe heat exchangers or to U-pipe heat exchangers. This was found also to be strictly coupled to the flow direction, the fluid flow direction. We also find that the heat going through the central pipe, which is the insulated central pipe, was almost 0 during all the tests, evidencing that the insulation properly worked and that there was no shunt flow between down and upgoing fluids. So here, just as an illustration, I present the temperature profiles for two of the tested cases, low flow and a relatively high flow, giving you a picture of how the temperature distribution looks like for these tests. We can see that the very low flow rate is when we start to see actually a shunt flow. Otherwise, the insulated pipe showed a good performance. The interpretation of these tests was done in the following way. I used the thermal recovery period between the first test and the second test to determine the ground thermal conductivities. And this thermal conductivity was put as an input for the calculation of the borehole resistance in each of the tests, 1, 2, 3, 4, 5, and 6. So the thermal conductivity of the ground found along the depth is according to this result, very high or higher thermal resistance at higher depth and decreasing with depth. And this, as I said, is put as an input to the calculation of local borehole resistances, which are plotted for each of the tests and each of the sections. And you see that there are, in average, they are in average about 0.04, but they change somewhat with the tested conditions. As an example, we could compare the conditions tested in test 2 with test 3, where the flow rate was constant between these two tests, but the power level was increased significantly. And then we can see that the thermal resistances in test 3 are somewhat lower than those in test 2. And this is attributed to the natural convection effect outside the pipes, which was also seen in U pipes. And many other implications which I think I will not go more in detail. The conclusions of the pipe-in-pipe heat exchangers are the following. Local thermal conductivities were found to be large in the upper sections of the borehole. Almost no thermal shunt occurs in this heat exchanger. And this is evidenced by the temperature in the central pipe not changing so much. And as the fluid enters the borehole heat exchanger through the peripheral pipes, the heat flow through the ground is uneven, being highest at the top. And this is a phenomenon that was also seen in some results not published, not shown in the presentation, for another heat exchanger type or multi-chamber type, which I also tested. So the flow regime in the peripheral pipes, in these little pipes, is laminar. And although the borehole resistance was found to be 0.04. It's important to remember here that this borehole resistance accounts for the temperature inside the central pipe, which in case of a perfect insulation is actually not really thermally connected to the borehole wall. And an indication of natural convection in the groundwater was also measured in multi-pipe borehole heat exchangers. I think this is my last slide, and I thank you very much for listening and coming to my presentation. I would like to take the chance also to thank all the companies and institutions sponsoring this project for making all this possible. Thank you.